using the dates. Today is 18, and I wrote 19, and it was also for the previous lecture. So don't pay attention to the dates, this is always important. Any questions from the previous lectures? Anything remain from the previous lectures? I know that there are many things that are just mentioned superficially, but I think that you can go through the tutorials. And also, I recommend you to start one of the books. My preference is the last reference that I mentioned in the book from Oppenheim. It's one of the best books you can refer to. Everything is clearly mentioned, everything is completely together with examples. So I think it's perfect if you just go through that. Because we are actually explaining the ideas, I think it's not something that takes a lot of time from you. It's okay. So finishing the DSP theory today will be important. Let's capture the screen. Everything that I write it down on the blackboard, I already mentioned whether it's something that relates to your exam or not. Because sometimes I just need to clarify some idea, and I'm writing something on the blackboard. But some of the ideas, for example, there are many things that I'm trying to explain today on the blackboard, and they are just for your information. Just put it there. Great. Okay. Welcome to the fourth lecture of DSP. So in this slide, I'm trying to recapitulate all the transforms we have studied so far and categorizing them into the continuous, for the continuous signal, discrete signals, periodic and aperiodic signals. So we already know from the bachelor courses, undergraduate courses, that when we have a signal which is continuous and periodic, we can represent this signal based on the Fourier, the sinusoids and the cosines coefficients, which we call it as a Fourier series. And in general, we show them by Fourier series. When they are aperiodic, we also know, I think at the beginning of the lecture we explained about the continuous time Fourier transform. So when we have a continuous signal which is aperiodic, we can use the continuous time Fourier transform, which in general is represented by, for example, if the signal is x of n or x of t, so it's the continuous in time. So the representation in the frequency domain, the CT of t, will be represented by x of j omega. And we know that the omega, or the frequency, is in the range of minus infinity to plus infinity. So it can have any values for, we can have every value for the frequency. And so when we go to the discrete signals, which in the time domain is represented by x of n, then for the periodic and aperiodic signals, we have different representations. For the aperiodic, I start with, we call it discrete time Fourier transform, DTFT, which we represented by x as a function of e to the power of j omega. But this omega is between minus p and p. So the highest frequency is p, and the minimum frequency is around 0. And when we say minus p and p, it means that we have, for the real signals, a symmetry around the origin. So the highest frequency in the DTFT domain is p. That's the highest frequency. And the minimum frequency is 0. So we should know that whether the signal has any values for the higher frequencies or the lower frequencies, or the signal is just limited in band pass frequency from some omega 1 to omega 2. Then we explained DFT, but beforehand we started with discrete Fourier series, DFS, which both of these representations work for discrete time periodic signals. X of n, which they have the period, for example, in capital N, so such that x of n equals to x of n plus n. So that's called the main period. But it can also be every multiplication of n. For this kind of signals, we explain the discrete Fourier series, which is the Fourier coefficients. So the harmonical Fourier coefficients, I mean the sinusoids coefficients. And when we restrict it to just one period, we call it as discrete Fourier transform. And we represent it by x of k. The coefficients are shown by x of k. So if the signal is assumed to have length n, for the discrete Fourier transform, I mean the corresponding coefficients in the discrete Fourier transform, we have length of n xk. So xk, which k goes from 0 to n minus 1, it means n number of the coefficients are active. And the signal is also the same size, n number of the taps for the signals. Then we explain a fast algorithm for implementation of the DFT, which was called fast Fourier transform, FFT. And FFT is an algorithm that leverages two important facts from the bases which are used in the DFT domain. And these are based on the symmetry and the conjugate facts, which already holds in the basis, e to the power of j omega, which omega for just some number of the equidistant values of, so we better say 2 pi over n multiplied by k, so k goes from 0 to n minus 1. So we have equidistant subdivisions of the frequency band, and there are two facts holding for those for the bases for this Wn, which we called it as a twiddle factor. There are two facts I already explained in the slides, and I will explain it probably if you have time. I will explain it in the end of the lecture for 1-2 minutes. So, based on them, we could actually come across with an algorithm which is called FFT algorithm. It's much faster than the DFT. So if the DFT takes something like n squared number of multiplications, for the FFT algorithm, we have actually n log n on the base of 2 number of the multiplications. And it means that if you have 1,000 taps for the frequency division, if you use the normal DFT, what you will have is 10 to the power of 6 number of multiplications, but here you just have 10,000. And it's 100 times, so it's 100 times faster. Okay. One more thing to mention again is about the convolution. We should know that when we are doing something in discrete domain, for example, when we are doing the DFT or any of the properties, we are actually seeking for any of the properties which holds in the DFT domain, we should know that everything is periodic. What I mean by periodic is that you have a window that works for 0 to n minus 1. And the signal that you can see is periodic over, from both sides. So everything should be observed from that window, but we should take care about the periodicity of these, of the signal or the filter that we see from that window. For example, when we do the convolution in DFT, in computer, for example, using the MATLAB, the convolution is actually done in circular form. So it's a form of the periodic convolution. So it's quite different with the regular linear convolution that we normally know from the continuous time convolution. So one of the properties of DFT is that, that the property itself works the same as what we had in the continuous time signals, but the way that we go through the convolution is quite different. So we have to discriminate between these two convolutions that we see in the DFT domain and what we already had in the CTFT domain or in the continuous time domain. Here in DFT domain, exactly in the same way that we had in the continuous time domain, we have a convolution of signal with a filter like h of n, or impulse response, which is h of n. If this is the convolution, then in the DFT domain we have, sorry, it should be multiplication. So I will just correct it. Then in the DFT domain we have the multiplication of the DFT version of the signal times the DFT version of the impulse response. So the convolution gives us the multiplication. But the convolution that we have in DFT domain is different from the convolution that normally we know as the linear convolution or the regular convolution. So when we are in the DFT domain, we are actually doing everything in a circular case or cyclic convolution case. As an example, in the right side of the slide, you'll see, for example, we have x1. It's a kind of windowing function, for example. The major window is from 0 to n minus 1. The period is n, so the signal is periodic with period n. But the active taps are from 0 to n minus 1. And we have x2 of n exactly in the same way. And now what we're trying to do is to convolve x1 with x2 using n taps. So convolving with n coefficients, with n taps. How this convolution is done, we actually should take care that the signal from 0 to -1 is periodic. We have to look for we have to observe the problem as it is a circular a circular signal or the periodic signal. Then, for example, in the normal convolution, the regular convolution, what we have to do is, if, for example, if we have a signal like this, for example, this is the x of n, and we have such kind of filter, h of n. In the normal convolution, if we do just the normal convolution, assuming that this x of t and that's the y of t, in the normal convolution, what we do is in the regular convolution, x of t convolved by h of t, what we do is first we try to get h minus t, which is symmetric around the origin, so it's something like this. And then what we try to do is we try to gradually push this signal inside on the right hand side and calculating the part of the signal which are overlapping. So this surface which is overlapping. So this is for without any movement, we have this. If we start to have a movement, for example, with tau, for example, then we have signals like something like this. And this part will have overlapping with this part. So we try to take the overlapping of this. That's the convolution. Then we start again to move it forward. Then the overlapping becomes more. For example, this part of the signal overlaps with this part of the signal. So the entire signal. And then, after some movements, for example, we reach to the part which the signal comes here, the filter comes here, and the signal is here. So there's no overlapping, and the result will be 0. So the gradual movement of this h minus t, so it's actually what we try to do is h minus t, then we start to move it on the right hand side, which is changing the t to t minus tau, and then the tau is increasing from 0 to something, or from minus infinity to infinity based on the length of this h of t. Then we try to actually do the integration. We integrate, it means that we are calculating the surface that we overlap between these two. And we try to move it forward. So from minus tau 0 to plus, for example, tau something, and we have values. And after the tau e, the result will be 0, for example. So we move this signal, the h of t, as a signal or as a system, doesn't matter. We move it on the right hand side until we have no overlapping with the main signal. And if the signal is limited in the time, then for sure this tau of e will not go to the infinity. So that's the regular convolution. And just as a reminder, if this signal goes from 0 to L1 and the system is from 0 to L2, the convolution, we have values from 0 to L1 plus L2
minus 1. If no, assuming that we have number of attacks that for the signal L1 and L2. So we have from 0 to L1 plus L2 minus 1. So the length of the convolution is more than the length of each of the individual signals, xt and h of t. That's the regular convolution. When we have the circular convolution, the story is a bit different. There's nothing to clean up blackboard. So in this case, what I'm trying to do is, I'm trying to tell you that you should assume that this signal is periodic. So it means that you should see the signal x of n, h of n and x of n like this. Assuming that they both have the same, I mean that they have the size of n, then you should look at the signal, this n minus 1, 0 to n minus 1. Then you should see both of them as a periodic signal. And they go from both sides to infinity. But the window that we are looking, observing everything, is this window. I should actually make it a bit. And what makes the difference? The difference comes from this fact that if it's periodic, then when you do the h minus n, so you're actually creating a symmetry of part of the h of n. So what you're trying to do is actually, you make this inverse just like this, but everything is again periodic. When you try to push it forward, what happens is that it's not 0 that comes from the left-hand side, but it's a part of the signal or the filter which is coming from the left-hand side. So if the signal, for example, h of minus n, I'm talking about the h of minus n, is something like this, and so on. When you're pushing the signal, what happens is that, you know, this signal is coming from this side, and you have the other values. So you have overlapping this side and this side. Then it's again coming inside. So you have this and this. So you have overlapping from here and here. And pushing forward. But what you're looking is just inside the window, here. The only part that you're looking to the convolution, circular convolution, is from this window. What happens is just inside this window. But you should look at the h of n and the main signal as a periodic signal. That's quite different. So, as an example, if you have two windowing functions like x of n and x2 of n, then the convolution is actually looking like this. The final convolution will be like this. It doesn't mean that it's the main convolution. It's actually a periodic signal, but we are actually skipping all the periods. The periods are on the left-hand side and the right-hand side. I was just observing the main window. So we take the main window as the convolution, the circular convolution between x1 and x2. So that's the cyclic convolution. You have to make it, I mean, you have to practice it using the, you should go to the book, for example, to practice it by hand to see for some specific signals what exactly happens, so that you can dominate the circular convolution and everything's circular. But the point of question is that when we are doing the MATLAB examples, we need, for example, linear convolution. But we know that MATLAB does everything in the frequency domain by the FFT or the DFT. And we know that DFT or FFT is a cyclic word. What happens if we want, for example, a linear convolution or a regular convolution, but the computer is doing everything circular? So there should be a kind of relation between the linear one and the circular one that we have to figure it out. That's the question here. So if you really want a linear convolution and not the circular convolution in computer for any kind of, for example, LTI systems, then how to do that when you have just a circular convolution and the solution is here. That's the structure if you want to have a linear convolution. So we have x of n as the samples from xt, h of n as the samples from h of t, which is the impulse response or filter. And we have, for example, even different lengths. One is the length n, and the other one is length m. In general, they should have, or they could have different lengths. What we try to do in that sense is to make the lengths equal. So we try to zero pad the signal and the filter such that they both have the same size. So for this one, we add n-1 zeros. The other one, we add n-1 zeros. And we look at the signal in the window with a size of n plus n-1. We do the DFT, and then we multiply it, just as a regular convolution. We multiply that, and we do the n plus n-1, I mean the same window size. We do the inverse of the DFT, and what we get is actually a linear convolution between h of n and x of n. So even though in MATLAB it's just working in a DFT domain, with circular convolution, we are able to get the linear convolution of these two signals with different sizes. Any questions so far? Okay. So I explained about changing the sampling rates. And I said that we have two theories, downsampling theory and upsampling theory. With downsampling theory, what we try to do is to lessen the sampling rate from what the signal has already been sampled with. For example, the sampling rate from an analog signal is f of s. What we try to do is we try to understand what should be the signal if the sampling rate was f prime, which is less than f of s. For example, you have 16 kilohertz of sampling. What should be the signal if you had 8 kilohertz of sampling? The quality or the performance of the signal, or how it looks like. So the theory of downsampling, which I already explained, is a system, is a structure that contains a pre-filtering, a low-pass filter in the beginning. And what was that low-pass filter for? It was actually to avoid the aliasing. So if you don't use that, then after doing the downsampling, because we know that the downsampling is periodic. Everything is in the Fourier domain, discrete Fourier domain, and it's periodic. So if the bandwidth of the signal is more than what you're extending, I mean, you have a signal with the initial band frequency of something like this. For example, E sub omega. When you downsample the signal, and here is omega b and minus omega b, when you downsample by the size n, what happens is this signal is expanded. Both it's expanded and it's periodic. So the 2 pi goes somewhere here. So you have so you have something like this, which goes from both sides. So you have part of the signal which are overlapping, and this overlapping screws up some part of the frequency band. So that you will miss part of the information which is already in the signal. Even if you filter the signal in the end, the filtering like this, again, you have part of the signal, the information of the signal, which is already lost. From here to here is lost. So this part of the information is already lost. In this window, this part of the information is already lost. Just this part is reliable. So that creates a problem. That's why we try to, in the beginning stage, we try to have a low-pass filter, and that low-pass filter avoids the aliasing which will happen after this expansion is periodic. The next system was upsampling. So the low-pass filter and downsampling together is called decimation. And now we have the upsampling. So the upsampler together with the filter is called interpolator or interpolation system. So the idea in upsampling was to add some zeros to the signal So in upsampler, what you do is just you add some zeros to the signal. If this is your signal, for example, then when you do the upsampling, for example here, you want to upsample by the ratio of 3. It means that every 2 samples you need to add 2 zeros. So you make 2 zeros here, then you have this sample, then you have 2 zeros, then you have this, then you have 2 zeros, then you have this, 2 zeros, and so on. So this is the upsampled version of the x of n. This is x of n. This one is xu of n with a ratio of 3. And for downsampling, what you do is removing some of the samples and then crunching the samples together. So for the downsampling, if the same signal you have for the downsampling, with the ratio, for example, ratio 2, you keep the first one, then you skip this, and you put the other one close to this one. Then you skip this, and you take this one. You skip this, and so on. This is the downsample. So here by adding zeros, you're just expanding the signal. So x of n and this xu of n, or expanded version of the n, is just some zero padded or zero added signal which is corresponding to the x of n. So the question is that giving you any kind of new information or not? So you were trying to increase the number of the sampling. So you had, for example, 16 kilohertz of sampling, and you want to go to 48 kilohertz of sampling. 3 times more. In general, it means that if the original signal was taken by the sampling of 48 kilohertz, the resolution of the signal should be much higher than the one taken with 16 kilohertz. But the question is that true to say that just by adding zeros, a number of the zeros based on this increasing the sampling rate, between any of these two taps or active components of the signal, does it give you any more information to understand exactly what's happening in the 48 kilohertz? Or it's just an expansion? So the answer is that it's just an expansion. So that's something that increases, actually compresses the bandwidth in the frequency domain, but it will not give you any more information unless you do this filtering, I mean the post-filtering, which is a kind of smoother. So that post-filtering, what it tries to do is, you know that the low-pass filter I already presented in the previous lecture, or maybe two lectures before, that an ideal low-pass filter corresponds to a sinc function. That's something that corresponds to the sinc function. So what we're trying to do using that low-pass filter, which in the time domain is corresponding to a sinc function, is using that sinc function as the interpolator between any two samples of the signal. Exactly. So using that low-pass filter in the end, what we're trying to do is not just resorting to these zeros which are padded to the signal and extended the signal, but also what we try to do is we are actually interpolating sinc functions over any of these values. And the final result is the interpolation using the sinc function. And as it's mentioned here, the xi of n, which is the upsampled version of the signal, is the low-pass filtered version of xn. So we know that h of the filter is a sinc function. We know how it looks like. So the interpolated signal is actually x of k. So any of those values of the signal, the DFT of the signal, times the sinc function, which is actually, I mean, the sinc function is actually scaled and shifted and averaged. That's what the interpolator does. And hoping that the signal is taken from natural phenomena, it's not a noise. Normally the natural phenomena, they actually have a kind of relation between the samples. It's not like the noise to have independent samples. So every sample in the noise, random noise, is independent from the previous one. But for the signal, it's not like that. You have always a correlation between different samples. So it means that for the natural signals, normally it doesn't contain a very high frequency. Because if it contains a very high frequency, then it's filtered out here in the low-pass filter in the end. If it's coming from a natural signal, using this interpolation is somehow like the smoothing of the signal. So this averaging and smoothing using the sinc function works. And it gives you the upsampled version of the signal, approximately. It's not just, it's not just mentioned in your mind that it's not like to have the analog signal taken with a sample of 48 kilohertz. There is always an error. But it's a mechanical way to simulate what should be the signal in the 48 kilohertz if it's originally taken with 16 kilohertz of sampling. The closest samples should be using the upsampler. Okay. Using this sampling rate conversions, we will see in the filter banks and many other structures that they are very useful using upsampler, downsampler, or a sequence of upsampling and downsampling systems. But there are two identities which are called noble identities. They are very important. That's why I have mentioned them here. And there's a question coming afterwards. You can solve this question I will ask the tutors to put this question actually as one of those, one of the problems that you have to solve it. It's very simple. So I'm explaining the noble identities and then the problem. So the noble identities, what they say is, if you have a signal x of n, you pass the signal through the downsampling with the ratio of m, then you have something like xa of n. And then if you pass it through a filter, which in the z domain is mentioned, they're represented by h of z, then you have the output ya of n. It's exactly identical as to say that we have x of n passed through a filter hz to the power of n, and then this signal, the coming outcome signal of this, is passed through a downsampler by the version of n. What is h to the power of z? So h of z is here. You know h of z. That's h of z. But when you say h z to the power of n, it means that you have to replace z with z to the power of n. So here it means h of n, z minus m. In case that hz and hz to the power of m is like an FIR filter, so we can demonstrate it using a polynomial. In this case, for example, we have h0, h1, z minus 1, h2, z minus 2, and so on. In this case, we have h0, so this here is just a DC value. There is no frequency, but it's just a DC constant value. Then we have h1, z minus m. Then we have h2, z minus 2m, and so on. Intuitively, it means that we have m minus 1 zeros padded to h of z samples. Do you get it? So, if you add m minus 1 zeros between any two samples of h of z, it's just like you say hzm. So hzm is the expanded version of h of z. So, these are identical. These two systems are identical, and the answer is the same. So the same signal in the input will give you the same signal in the output. Analogous to the first one, for the upsampler we have the same identity. Something pretty the same. So if we have xn pass through a filter, h of z, and then pass through an upsampler, it's completely the same as to say, first of all, give the signal to the upsampler, and then pass it through a filter, which is expanded by L. The result is the same. So these identities, noble identities, are called noble identities. In the book, it's mentioned as noble identities. They are very useful when you want to implement the polyphase filters and the filter banks, polyphase filter banks. The filter bank is quite identical to the wavelet. So, the question I posed here is, assuming that we have a signal x of n, and we have an upsampler m, and downsampler n, with the ratio of n, and we get the signal in the output y of n. What should be the condition between m and n such that we can easily replace these two blocks? That's the question. You should go through the upsampling and downsampling equations in the frequency and time domain. You know that already. You have in the slides, I think in the previous lecture. And to figure out what is exactly the relation between M and N that gives you this property. So for the next Monday or the next coming tutorial, that the day that you have to present your solutions, please add this problem to whatever you have.